Okay, and now I'd like to welcome Leonardo Solidoro to the stage to talk about QFT simulators and superfluid helium vortex flows.
So, hi everyone, thanks for having me. So yeah, basically this is the first presentation where we present our experiment when we try to simulate QFT anchored spacetime using draining vortex in superfluid helium, Helium-4. Yeah. So in particular, I will focus more or less on the theory background as Silke more introduced, and on how we can characterize and detect such surface wave propagating on top of our system, such that we can study this analog gravity effect. So, as Silke introduced, the idea of analog gravity is that we can map the dynamics of perturbation propagated on top of continuous system to the dynamics of fields on curved spacetimes. And there are many systems that exhibit this kind of behavior. For example, the original UNRO paper proposed this perturbation to be sound waves, so pressure and density perturbation. But the same thing happens when gravity surface waves are concerned. So the model that we study is basically modeled as a fluid propagating between a basin and a free surface in the shallow limits. So in the hypothesis that the length scale defining the heights of the field is much lower than the typical length scale of the waves. Particular, the physical system we consider is made of an invasive fluid flowing irrotationally. So invasive fluid means the governing equation are basically the Euler's equation, and irrotational means we can introduce this scalar field quantity called the velocity potential, from which we can retrieve the velocity. So by perturbing the equation of first order, we get this couple of equations for the perturbation of the velocity potential and the height field, which can be recast as an effective Klein-Gordon equation for these perturbations, whose metric is given in terms of the velocity flow of the field, and it depends on the speed, propagation speed of the perturbations, which can vary as the basin changes. So this is basically the idea behind it, but we focus on a particular class of flows, vortex flows, that in general have this form. This is the general form of an irrotational flow satisfying all this equation in azimuthal symmetry, so in cylindrical coordinates, where this is the radial coordinate, this is the angle, and D and C are two constants. So following this description in terms of the metric, we have an effective space-time whose line elements reads in this way. But despite the technicality, we can identify two regions and surfaces which are relevant for our analogy with black holes and gravity. Particularly, we can identify an horizon that is defined as the surface within which the velocity of the fluid exceeds the propagation speed of the perturbations. And this way, this perturbation cannot propagate outward, and so it creates an effective causally disconnected region, as in an event horizon for us for a black hole. And in particular, if this constant here, C, the circulation is not zero, we even can identify an ergo region, which is a region within the module of the velocity field exceeds the propagation speed of the waves, and acts as an ergo region for our rotating black hole. In particular, this kind of flows, as Silke mentioned, has been established here in Nottingham in our big vortex, big bathtub in the lab, and they've proven that phenomena related to the presence of an ergo region, namely superradiance, for example, what as predicted in black hole physics, find their place even when surface waves propagating on water are concerned. But of course, finite viscosity prevents more subtle, more evasive phenomena to be detected. So this is why people moved to quantum fluids. So these fluids, quantum fluids are in general multi-particle systems where most of the components are in the same state. In particular, as an example of these are Bose-Einstein condensate, where most of the atoms composing the boson composing the system are in the ground state. Such coherence, phase coherence that emerges from this configuration allows us to describe the system in terms of a complex order parameters. And in turn, we can, remarkably, the dynamics of such system can be mapped to the dynamics of a invasive flow by identifying the velocity with the gradient of the phase of these order parameters. And with this identification, we have that naturally such system have an irrotational flow, which is one of the hypotheses that we need for analog gravity to work in any simply connected region, of course. But circulation can still be present in such systems, but it can appear around some topological defects in the system, and remarkably, it is quantized. There is an integer multiple of a circulation quantum, where m is the mass of the boson composing the system. Among the different quantum fluids that one can consider, such as Bose-Einstein condensate or polariton fluids, we, as Silke mentioned, chose to work with Superfluid Helium-4. Remarkably, Superfluid Helium allows us to build a macroscopic system over which we have a full control of the characterization of the surface. And of course, our system can possess a free surface on which we can construct and study the analog theory. Superfluid helium is quite a peculiar quantum fluid because superfluid helium is liquid helium when below 2.17 Kelvin, when it undergoes this phase transition and acquires new features. In particular, it's a quantum fluid because it presents this kind of quantization of circulation. And remarkably, when you start steering it or introducing some circulation, you will see the emergence of such a topological defect, has line defect propagated throughout the system, each of those carrying one quantum of circulation. Even if as we approaches 0 Kelvin, it becomes a perfect superfluid, but at finite temperatures, when we operate, it behave or is phenomenologically described as a mixture of two fluids, a regular one, a viscous one, and an invasive one. Still, even if the perturbation the viscosity is not completely zero, it's still a very low viscosity system when we can study our analog gravity. In particular, let me just mention a remarkable property, caveat when dealing with quantum fluids. Because, of course, we have this macroscopic sample of helium and we steer it. We're introducing a macroscopic circulation, which well exceeds considerably the dimension of a circulation quantum. So we expect such system, if used for analog gravity purpose, to present a larger number of circulation. Still, the circulation is quantized, but the problem is that a vortex containing more than one circulation, carrying more than one circulation quantum is an unstable state, and it rapidly decays in a bundle of singly quantized vortices. And this is quite unfortunate because they are their own dynamics and they tend to repel each other and spread throughout the system. This is quite inconvenient for us because even if the surrounding flow is irrotational, the spreading of these quantum vortices introduces or imprints solid body rotation to the system. So effectively, we can recognize the presence of such vortices as a solid body rotation which is imprinted in our flow. And this spoils the analogy with an effective spacetime because irrotationality is required as an hypothesis. We managed to build a setup which consists of a stationary draining vortex. So when we confine such the bundle of vortices in the center outside the experimental zone, as Pietro will show you later. Now I will present to you how we detect the waves which propagate on our sample. So the idea behind we can detect with enough resolution both in space and time, and by sampling the whole surface of the fluid, is by exploiting this synthetic shielding imaging, which is based on the idea which every one of us maybe have experienced. Then when we look at the fluid from above with some known background below it, when where the surface is perturbed, is not just flat, these waves will produce an effective distortion of whatever is below it. And the idea is that if these waves are small enough, we can parameterize this distortion as an effective displacement which happens locally in this background below the waves. So if this is our background, as seen when the wave passes by, this is it can be parameterized as the background of the background without the waves, so the known background, but with the introduction of this displacement vector, which acts locally. So the idea is that we can obtain the information or reconstruct the surface by obtaining, getting numerically this displacement vector. For this, we use this technique called fast checkerboard demodulation, which exploits a two-dimensional periodic pattern. And the effect of this local displacement will be modulation in the phase on this known checkerboard pattern. And by analyzing it using this pattern, we can extrapolate the component of the displacement vector immediately. In particular, this is one of our a frame as of our experimental setup. So this is the pattern that we use. That is when the vortex is created. And you can imagine that on top of this, there is just superfluid helium, which is almost perfectly transparent. So what we do is that is recording an image of the imperturbed surface, so without any waves on it. And by fast Fourier transform, we can extract these carrier waves, which are the frequencies associated with the periodicity of our pattern. Then when the wave passes through, the FX is to modify locally the FFT or the spectrum of our images. So we can easily identify the peaks corresponding to carrier waves, and the effect of this perturbation with just to modulate nearby these peaks, the spectrum of the image. So by identifying these two peaks and the modulation introduced by the displacement vector, we can just extract numerically the phases for each pixel as detected by our camera. And since we have two carrier waves, because we have two perpendicular modulation, we have just a system of two equations for the two components of the displacement vector. So once we get the two components, we have this relation which gives us the gradient of the height field in terms of this displacement vector. This is just the distance between the surface and the pattern, and this is the ratio between the refractive index of the medium above the liquid and the liquid itself. So by integrating this formula, we are able to reconstruct the surface of our sample. This is an example. And this is more or less how we reconstruct the surface, and then we to facilitate the analysis that Pietro will present you. So of course this method has some pros and cons. The pros is that this is a very non-intrusive method. We don't need to introduce any external body to the sample, because usually when liquid helium is concerned, some flow visualization technique involves the introduction of particles in the fluid, which spoils the sample. and can even affect considerably the flow itself. Then what's remarkable for us is that with this method we look only at the surface where our physics, our prediction of analog gravity are relevant. Unfortunately, there are a lot of parameters that enters in this with this technique. For example, the resolution of the camera versus the resolution of the pattern, all of these. So this makes kind of very hard to predict a priori the performances of our reconstruction technique, but we are working on it by performing some numerical simulations. And eventually we want to reduce the circulation injected in our system and be able to resolve individual vortices. But this method is not well fit for it because it has a macrometric resolution. We can identify perturbation up to the micrometer scale. But fortunately enough, as Vitor will present to you, we are moving toward a new technique called digital holography that will allow us to probe even this new regime. And yeah, that's it. Thank you.